All right, guys, in video B, we're going to learn how to graph what these logarithmic functions look like. So we're going to do the same thing that we did on that first page of the exponential functions, kind of give you a rundown of all of the little features and different things that you'll need to know from the logarithmic function. And then we're going to use 3 points, same way as we did with those 3 points from exponential functions, okay? So here's the info that we've got. Parent function looks like this. Y equals log base b of x, the same thing we were working with before. What type of graph is it? It's continuous, it's 1 to 1. Okay, it might be increasing, it might be decreasing. We've got 2 different ones. The domain, okay, here I'm going to flip you guys back to the first page that we had when we were graphing the exponentials. Okay, so remember, I told you that exponentials and logs are inverses of each other. So these 3 points that we have when we were dealing with the exponentials, all of the x's and y's will trade places. When they trade places, we'll have an inverse function. So if all of the x's and y's trade places, that means their domain and range will trade places. Okay, so now instead of the domain being all reals, the range of log functions will be all reals. And instead of the range being just the positives, the domain will be just the positives. Okay, so all of this stuff is coming from the idea that logs and exponentials are inverses of each other. So that main idea is very, very important. So I'm even going to make a little note right here. So these functions are inverses of exponential functions. So everything that we know about exponential functions, we just swap the x's and y's, and we'll have all the details of our logarithmic functions. So the domain are just the positive real numbers. So just positives, but then the range is all reals. So remember this weird double R, that stands for all reals. The asymptote of exponential functions was the x-axis, so swap everything, and the asymptote of these will be the y-axis. The intercept of the exponential functions was the point 0, 1, so that means the intercept on logarithmic will be the point 1, 0. Okay, so let me write down here all of the points that we should be expecting. So on a function y equals b to the x, remember you've got these 3 points that you will see on every single function. You've got -1, 1 over b, you've got 0, 1, and then you've got 1b. So if you have those 3 points for any exponential function in this form, if we swap and do the inverse function, remember because these functions are inverses of each other, the x's and y's will all just trade places. So that will be 1 point, just swap these x's and y's. This will be another point, again swap these, and then this will be 1 more point. Okay, so our graph, I can give you a quick sketch of what the graph is supposed to look like. So the original, we're going to have 2 different functions. We're going to have one for a base that is greater than 0, for a base that's greater than 1, and we're going to have a second one for a base that is somewhere between 0. This is bigger than 1, this is somewhere between 0 and 1. So if I plot this point, 1 over b, -1, will be some sort of fraction, and then down here at -1, so like that perhaps. I have the point 1, 0, which is right here, and then I have the point b1, so wherever b is, whatever the base is, maybe it'd be somewhere like that. And remember now my y-axis is an asymptote, so it's going to kind of drag along that y-axis, and then it will look something like that. Okay, so that's what my logarithmic function looks like if my base is bigger than 1, 2, 3, something like that. If my base is a fraction, when I go to plot this point, the reciprocal of a fraction will actually be a whole number, like this. So I will have 1 over b, even though that'd be a positive number, somewhere over here. Let's say that's b. So if b was a fraction, 1 over b would be over there. So we'd have a point somewhere like there. We always have the point 1, 0, so right about there. And then we've got the point b1, which remember b is now a fraction, so it's going to be somewhere like there. And again, the y-axis is an asymptote, so this one's going to be kind of flipped upside down. So it'll hug along the asymptote and then curve like that. So like this if the base is bigger than 1, like this if the base is between 0 and 1. The really big important part that you have memorized, just like with the exponential function, is you need to know those 3 points. If you know those 3 points, you'll be okay to work from there. So let's try some out. Okay, so we're going to graph a base bigger than 1 and then a base between 0 and 1 just to kind of get the general picture. So our 3 points, and I'm going to write them again up here. We should have the point 1 over b, negative 1. So this is the reciprocal. We've got the point 0, 1. I'm sorry, 1, 0, sorry. And then we are going to have the point b, 1. So we've got those 3 points to go off. You will see it every single time, no matter what your base is. So our 3 points, our base is 3, so we're going to have 1 over 3, negative 1. We'll have the point 1, 0 every time, every logarithmic function, and then we'll have the point 3, 1. So all we have to do is plot those 3 points, connect the dots. So we will have, if that's 1, we'll call that about 1/3 down at negative 1. We got the point 1, 0, and then we have the point 3, 1 right about there. So all those points, connect those. We're going to get in the habit of writing the domain and range as well. The domain, as you can see, none of my negative x values are touched over here. It's just the positive values of x. But for the range, my arrow goes down, my arrow goes up. I will eventually hit every y value that I could ever hit. Okay, let's do this base of 1/4. So my 3 points that I'm going off of, I have the reciprocal of my base and negative 1. So the reciprocal of 1/4 is 4, negative 1. I always have the point 1, 0, and then I have my base, comma 1. Okay, so 1/4 and 1. So I'm going to plot those 3 points. So I have the point 1, 2, 3, 4, down at negative 1. There's my first point. I always have the point 1, 0. And then I will also have the point 1/4, positive 1. So always just approximate with those fractions. Do the best you can. So it's hugging along this y-axis. That's its asymptote, and then it goes like that. Okay, so my domain, still positive values of x. It's not crossing over this line here. And my range is all reals. Again, the arrow keeps going up and keeps going down, so I will eventually hit every y value that I can. Okay, so let's write down these transformations. Very similar transformations to what we've seen with parabolas, square roots, the exponential functions. And we've got still a, h, and k. We're using the same letters. Horizontal translation is represented by h, vertical is represented by k, and the orientation and shape, that's affected by the a. So our horizontal translation, remember what that does is it's going to move up, horizontal translation will move left or right. So if I have an x minus h, remember it's counterintuitive, that will move h units to the right. And if I have x plus h, it will move h units left. Same rules that I had with exponential. Okay, if this k on the outside, if it is in fact a positive k, we will go k units up. And remember, y does exactly what it's going to look like, so plus actually does go up. If I have minus a number on the outside, it will take my graph k units down. Okay, and then orientation and shape, as always, a is a stretch or perhaps a flip. So if a is less than 0, my graph will flip upside down. To be more specific, we should say it flips over the x-axis. If a is bigger than 1, there will be some sort of vertical stretch. And if a is somewhere between 0 and 1, there will be a vertical compression. So same rules that we've seen now a handful of times. We're going to use all of these rules to adjust our new points. Okay, so we'll start with the old points, and that's just based on our base of 6, and then we'll do any adjustments that we need to have right here. All right, so our old points, so the points for just the parent function, just log base 6, will have the following points. I will have the reciprocal of my base, negative 1. I will have 1, 0, and I will have my base, positive 1. Okay, so now I need to write my 3 updated points. Okay, so my new points based on my transformation. So if I have anything in parentheses that's going to move left and right, as you see there's nothing in parentheses there. The -1 actually moves up or down. So none of the x values are going to change. It's not moving left or right, so my original x values that I started with will be exactly the same. Now this is going to multiply my y value, and then this is going to move it down 1. So whatever my old value was, I will multiply it by 1/3. So 1 times 1/3 is -1/3, and then -1 will be -1 1/3, or -4/3. Okay, if I start at 0, 0 times 1/3 is 0, and then down 1 would be -1. 1 times 1/3 is 1/3, -1 would be -2/3. All right, so these are the points I plot. All right, so I go to sketch these out. I have the point 1/6, so I'm going to approximate, -4/3. So 1/6, -4/3 would be maybe like there. I have the point 1, -1, and 6, -2/3. Right about there. Okay, so still hugging the x-axis. As you can see, what this 1/3 does is it very much flattens out my graph. We call that a vertical compression. It makes it so that it's not growing very quickly at all. That is a very, very slow incline like that. Okay, my domain and range would still be exactly the same. The domain would be x is greater than 0, and my range would be all reals. The range will always, always be all reals, no matter what. Okay, let's look at another adjustment. Okay, so I'm going to take a look at the base, which is 1/3, and I'm going to write the 3 points down for my parent function, which is log base 1/3 of x. So my 3 points, I have the reciprocal of my base, -1, I have 1, 0, and I have my base, +1. That's original before any changes were made. Okay, so remember what this one does is I am going to actually move 2 units to the left. Remember, x is counterintuitive. Okay, so I'm going to take whatever my x value was and go left 2 units. And then this is going to multiply the y by 4. The only thing that will affect the x is something in parentheses. Everything else will affect the y. Okay, I will say that again. The only thing that will affect the x is in parentheses. Any other changes will affect the y value. So my new points, I'm going to move all my points to the left 2. So move this to the left 2, I'll be at 1. Move this to the left 2, I'll be at -1. Move this to the left 2, I will be 1/3 minus 2. So that's -1 2/3. Okay, and next, what this 4 is going to do, there's no plus or minus out here, so it doesn't move up or down, but I multiply all of these by 4. So -1 times 4, 0 times 4, and 1 times 4. Those will be my 3 points that I am plotting. I have the point 1, -4. I have the point -1, 0, which is right here, and then I need to move a little bit over, so let's call that -2. I have the point -1 2/3, and then up to 4. So right around there. Alright, so this will kind of come down like this. Now this +2, that moved my asymptote over 2 units to the left. So now it's going to hug right along this line and kind of stretch down this way. Okay, that 4 stretched it out. So that's going to look quite a bit different than the one on the previous page where we stretched by 1/3. This one's going to be really tall. The other one was very compressed in. Okay, so let's quickly answer this last question. We've got this right here. That's our logarithmic function. This is find the atmospheric pressure in atmospheres at an altitude of 8 miles. Okay, so altitude is x. So we have p equals 0.8, and then we're plugging in 8 for our exponent. So I am going to type this into the calculator, and I'm going off of my phone. Okay, so we'll have 0.8, and then we will raise that to the 8th power. So that gives us this, let's say about 0.168. Okay, so that is our atmospheric pressure. Next it says write an equation for the inverse of the function. Okay, so all we're going to do is take this and convert it into log form. So we take log, and then the base is 0.8, and then we trade. So now p gets tucked in right here, and then x would be on the other side. So that is what our inverse function looks. That's just kind of like a little extra practice in converting back and forth between exponential form and logarithmic form.